Good morning. I'm Devasena. In this lecture, we are going to discuss about brain-machine interface (BMI). This topic is present in the subject medical electronics. Brain-machine interface (BMI). A brain-machine interface is a device that translates neuronal information into commands capable of controlling external software or hardware such as a computer or robotic arm. A brain-machine interface is also defined as a communication system that does not depend on the brain's normal output pathways of peripheral nerves and muscles. BMIs are often used as assisted living devices for individuals with motor or sensory impairments. BMI uses brain activity to command, control, actuate, and communicate with the world directly through brain integration with peripheral devices and systems. It is a new communication link between a functioning human brain and the outside world. These are electronic interfaces with the brain, which has the ability to send and receive signals from the brain. The signals from the brain are taken to the computer via the implants for data entry without any direct brain intervention. Purpose of using BMI. The purpose of using BMI is to provide a method for the people with damaged sensory and motor functions in order to use their brain to control artificial devices and restore lost ability via the devices. Main principle of BMI. Main principle behind this brain-machine interface is the bioelectrical activity of nerves and muscles. The brain is composed of millions of neurons. These neurons work together in complex logic and produce thought and signals that control our bodies. When the neuron fires or activates, there is a voltage change across the cell. It's approximately 100 millivolt, which can be read through a variety of devices. Let us discuss about neuron transmission representation. The electrical patterns obtained on the surface of the skull are the result of the graded potentials on the dendrites of neurons in the cerebral cortex and other parts of the brain, as they are influenced by the firing of other neurons that impinge on the dendrites. Graded potentials are variations around the average value of the resting potential. Thus, the EEG potentials originate within the dendrite potentials. Electric charges are transferred between one nerve fiber and the other through a dendrite of a postsynaptic neuron during the release of acetylcholine. A great number of these potentials are then summed to produce EEG rhythms. The discharge of a single neuron or single nerve fiber in the brain cannot be recorded from the surface of the head. Instead, for an electrical potential to be recorded all the way through the skull, large portions of nervous tissue must emit electrical current simultaneously. There are two ways by which this can occur. First, tremendous numbers of nerve fibers can discharge in synchronous with each other, thereby generating very strong electrical current. Secondly, large numbers of neurons can partially discharge, though not emit action potentials. Furthermore, these partially discharged neurons can give periods of current flow, which is undulate with changing degrees of excitability of the neuron Simultaneous electrical measurements within the brain while recording brain waves from the scalp indicate that it is the second of these that causes the brain waves. Brain computer interface. A brain computer interface (BCI) is a computer based system that acquires brain signals, analyzes them, and translates them into commands that are relayed to an output device to carry out a desired action. In principle, any type of brain signal can be used to control a BCI system. Types of brain computer interface. There are two kinds of brain computer interface. They are non invasive brain computer interface and invasive brain computer interface. Invasive brain computer interface. Invasive brain computer interface. That is, microelectrode array are implanted into the brain and connect tiny electrodes to neurons to measure their activity. There is a representation of the microelectrode array. Artificial intelligence is used to isolate the brain signals that the BCI devices capture, as well as synthesize signals back into the brain. Non-invasive brain-computer interface. There are several ways to develop a non-invasive brain-computer interface, such as electroencephalography (EEG), magnetoencephalography (MEG), or magnetic resonance imaging (MRI). An EEG-based brain-computer interface is the most preferred type of BCI for studying. Non-invasive brain-computer interface representation is shown here. In this diagram, we are seeing the LFP, spikes, EEG, ECOG waveforms. Electroencephalography. Electroencephalography is a method used in measuring electrical activity of the brain. The EEG signals can be picked up with the electrodes either from the scalp or directly from cerebral cortex. The EEG is measured from the surface of the scalp by measuring potential difference between the actual measuring electrode and reference electrode. Magnetoencephalography (MEG). Magnetoencephalography is a non-invasive medical test that measures the magnetic fields produced by your brain's electrical currents. It is performed to map brain function and to identify the exact location of the source of epileptic seizures. Magnetoencephalography representation is shown here. Here in this diagram, we are seeing the origin of MEG signals. Here, the electrical current, magnetic field, intracellular current is represented in this diagram. Brain-computer interface block diagram is represented here. In this diagram, we are seeing the signal acquisition block, pre-processing block, future extraction block, classification, that is the deduction block. Then we are seeing the application interface, the applications. From the applications, feedback is given to the brain. Signal processing section, multi-channel acquisition system. At this section, amplification, initial filtering of EEG signal is possible. Artifact removal takes place in this section. Spike detection. Incorporating spike detection will allow the BMI to transmit only the action potential waveforms and their respective arrival times instead of sparse raw signal in its entirety. Signal analysis. In this stage, certain features are extracted from the pre-processed and digitized EEG signal. Implant device section. The EEG is recorded with electrodes which are placed on the scalp. Here is a representation. Electrodes are small plates which conduct electricity. They provide the electrical contact between the skin and the EEG recording apparatus by transforming the ionic current on the skin to the electrical current in the wires. The implants must be monitored closely because there is a potential for almost anything when introducing foreign signals into the brain. External device portion. The classifier's output is the input for the device control. The device control simply transforms the classification to a particular action. Example is robotic arm. Here is the representation. Feedback device. Feedback is needed for learning and for control. Real-time feedback can dramatically improve the performance of the brain-machine interface. Advantages of brain-machine interface. Provides better living, more futures, more advancement in technologies, etc. Linking people via chip implants to super intelligent machines seems to a natural progression, creating in effect superhumans. Linking up in this way would allow for computer intelligence to be hooked more directly into the brain, allowing immediate access to the internet, enabling phenomenal math capabilities and computer memory. By this, humans get gradual co-evolution with computers.
Thank you very much for listening this lecture. For further updates, kindly subscribe this channel. If you like this video means kindly share this video to your friends. Thank you.